Okay, so here's our pink sheet. This is just kind of a picture representation of the different things that would make something not differentiable. So differentiable is another word for like if you could find a derivative or not. So this is why we could not find a derivative. So what does it mean to be differentiable? Let's go ahead and take the pink sheet and flip it over. We're just going to put some notes on the back. So to be differentiable at a point A, to be differentiable at a point A, let me see if I can zoom in. Nope, I'm already zoomed apparently. To be differentiable at a point A means that f prime of A, oops, that's not the end of the sentence, f prime of A exists. And remember, f prime of A is just notation that is a slope at a single point. So all that means is you're differentiable if you can find the slope at the single point. Then it's differentiable at that point. To be differentiable on AB, so this is the open interval AB, so I'm using parentheses, that means I'm not including the endpoints. To be differentiable on AB, the open interval AB, means that the function, that's gracious, means that the function is differentiable at every point on AB. So it's a smooth sort of curve where on that interval at every single point you could draw the little tangent line along the curve and you could find a slope at every single point. There's an instantaneous rate of change for every single slope, okay? Or every single point. And since we learned on the first 2 days of the unit, well, I guess this was supposed to be the second day of the unit. So since we learned the first day of the unit that the derivative comes from the slope formula, and it comes from taking the slope formula and turning it into a limit, it literally comes from taking it and turning it into a limit, then that means that differentiability comes from a limit existing. Do you guys remember what we need for a limit to exist? The left hand and right hand have to agree with each other. So differentiability comes from the limit definition, which means that the limit as x approaches a from the left. So remember, we talked about unit 1, when we were finding limits of functions, so those were y coordinates. This unit we're finding limits of slopes, so we're no longer saying that our outcome is a y coordinate, our outcome this time is a slope. So the left-hand slope has to equal the right-hand slope. If the left-hand slope and the right-hand slope are not the same, then that point is not differentiable. Okay? So that means we got to have some smooth curves. If the curves are not smooth, then you can't find the slope there because the left-hand slope and the right-hand slope would not be the same. So we're not thinking in terms of y-coordinates anymore. Now we're thinking in terms of slopes. Okay? All right. So if you flip the page over, reasons why a function may fail. Let's run out of lead. Maybe? No? Fail. This is why something is not differentiable. Fail to be differentiable. They call this a corner, a sharp corner. At 0, the left-hand slope and the right-hand slope do not agree with each other. You guys see that? What's the left-hand slope? What's the left-hand slope at 0? -1. Do you guys see how that slope is -1? Okay. What's the right-hand slope? +1. So if you tried to find the slope at 0, -1 and +1 don't agree with each other. Those are two different numbers. Now, last unit, if we were talking about y-coordinates, the y-coordinates agree with each other. They're both 0. But this unit, we're not talking about y-coordinates anymore. We're not saying the limit as x approaches 0 of f of x. We're saying the limit as x approaches 0 of f prime of x. We're talking about the slopes this time. Okay, so if I were to write this, the reason is that right here, the limit as x approaches 0 from the left of x prime of x is -1. On this side, the limit as x approaches 0 from the right of f prime of x, that's +1. Those two slopes don't agree with each other. And it's very easy to recognize in a graph you have a sharp corner. Smooth curves don't do that. They're so gradual that it's kind of the idea that we used to see in tables when we were looking at the y coordinates. You'd say like, oh, the left-hand y coordinate is like 2.999. The right-hand y coordinate is 3.001, and they're both approaching 3. Right? So a smooth curve does not act the same way a sharp corner does, and we could say the slope is approaching the same thing because it's kind of doing that decimal thing. Those sharp corners, they're not differentiable because we can't make a conclusion about that. -1, +1, those numbers are too far apart for us to say, oh, that slope in between is something. Does that make sense? Okay. A cusp, same idea, looks slightly different. Okay, same idea, it looks slightly different. All right, vertical tangent line. What's the issue for a vertical tangent line, do you think? Any ideas? You just put your hand up. What's the slope right here? Think about rise over run. Think about what would have happened for a vertical line. It'd be over 0. Change in y divided by change in x, your change in x is 0. So the issue there is not so much that your left-hand limit and your right-hand limit are not agreeing with each other. The issue there is that you're trying to divide by 0, and mathematically we just can't divide by 0. Okay? So the issue here is that with a vertical tangent line, when you do your slope is rise over run, your slope is a number divided by 0. That's the issue with the vertical tangent line. Does that make sense? Okay. A discontinuity has the same issue as a corner or a cusp. The left-hand limit of the slope and the right-hand limit of the slope don't agree. Actually, the slopes could agree, but it's just that it's discontinuous. So that's kind of the tricky part there. And then I like how they said other weirdness. That is the mathematical term for it. That whole oscillating idea is kind of where we can get some other things that are not differentiable. Looks like this. So if you put a point right here, right, and then you tried to take a tangent line and put it right up along that curve, it would be a vertical tangent. It would look like this. And then since it's a vertical line, vertical lines have the equation like x equals 0, right, or x equals 1 or x equals 2, and then the slope of that would be that undefined number. So you couldn't say like, oh, it has a slope of 0 or has a slope of 1. it has like an infinite slope, and we can't write that. Does that make sense? All right. I need someone. That's really fun. All right, go ahead and take the pink sheet and flip it back over. All right, so here is a theorem, and this theorem is really good. We're going to really like this, and we're going to use it on FRQs. So here is the theorem. If a function f of x is differentiable, goodness gracious. The spelling is hard today. That's how you can tell the headache is still there. Differentiable at x equals a, then f of x is continuous at x equals a. This is a big, it seems like it's a little thing that doesn't even matter, but it's a big deal because think about, we've learned some things where it was important to say first that it was continuous, therefore we could do something else. So there are some times when they'll give you like an FRQ or they'll give you a problem and they will say the derivative of it is this, and it's true for the entire domain or whatever. As soon as they say that, you go, oh, it's continuous. They didn't explicitly say in the problem it was continuous, but as soon as they said you could take a derivative, you go, oh, it's continuous. I can do all the other things with it that I was allowed to do with continuous stuff. Does that make sense? So like with the intermediate value theorem, we had to say it's continuous so we could use the intermediate value theorem. So you might end up working with a function where like you on your own don't know enough about that function to know if it's continuous on the interval, but as soon as they say it's differentiable on the interval, you get to say, oh, it's continuous too. So it is not uncommon in an FRQ for your first step to say differentiable, therefore continuous. That's pretty common to do, okay? And it's because of this. So I would circle this. This is something that on a test, in a brain fart moment, if you can see this on your pink sheet, you're gonna go like, oh yeah, I get to use that. That's nice. So if it's differentiable, it's automatically continuous. You don't have to say by theorem, blah, blah, blah. People literally say differentiable, therefore continuous, okay? And you don't even have to say it formal-like, because mathematicians, you could say diff, therefore continuous. And mathematicians are like, yep, that's right. And that is good justification, okay? They go for that. Differentiable, therefore continuous. Uh-huh. Uh-huh. Yeah. Because that is a loaded statement. That shows a lot of mathematical understanding, okay? All right. The contrapositive of that well, once I say it, then you'll go like, okay, that makes sense. If f of x is not continuous at x equals a, then f of x is not differentiable at x equals a. So contrapositive is just like, yeah, the opposite. If it's not continuous, then it's not differentiable. If it's not differentiable, that doesn't necessarily mean it's not continuous. But if it's not continuous, it is definitely not differentiable. That is for darn sure. Yeah. If it is not differentiable, that doesn't necessarily mean it's not continuous, because we saw from that first example, these are both continuous, but they're not differentiable. So just because it's continuous doesn't mean it's always differentiable. You can have those corners, you can have those cusps, oscillating graphs, those are continuous, but they're not differentiable. So continuity doesn't mean that it has to be differentiable, right? But if it is differentiable, it is definitely continuous. If it is not differentiable, it is definitely not continuous. Or if it is not continuous, it is definitely not differentiable. Does that make sense? Okay. Yeah, not, yeah. No, differentiable does equal continuous. That direction is true. Differentiable equals continuous. Continuous does not equal differentiable, though. Does that make sense? So maybe draw an arrow. Differentiable goes to continuous. Continuous doesn't go to differentiable. Yeah. It's a one direction type thing. Oh, I just said one direction. Oh, no. That was unfortunate. All right. I think that is good. Yes.
You can't like say just because it has a cusp, you can't say it's differentiable except for like x equals 0.
Yeah, so a lot of times when we talk about differentiability, a lot of times they're concerned about is it differentiable at every single point? And so we would say, yeah, except for at x equals 0. There's a cusp there. You're exactly right. Yeah. Yeah. Yeah, and a lot of people know that's what it means is like, kind of like with piecewise functions. We knew with piecewise functions that like they were differentiable. You could find the limit last unit. You could find the limit in most spots, but the spot that we were most interested in was like the one spot it didn't work. You know what I mean? Like the spot where you switched pieces. That like if x was less than this, if x was greater than this, that was the spot where it was the most interesting because the other spots were usually okay. So when you're talking about differentiability, you're mostly interested in, is there a spot where there's a corner? Is there a spot where there's a cusp? And that's the spot we're talking about because we do recognize that a lot of graphs act in predictable ways for most of the graph, and then maybe they have one weird little spot. And so that's the spot we're usually talking about, is like, is there one little spot? So a lot of times when you say, reasons why a function may fail to be differentiable at a point, we don't say it fails, it's like not differentiable, period. We say it's not differentiable at this specific spot because this. And that implication is it's differentiable at other spots, it's just not differentiable here. That was a really good question. I appreciate that. All right. Any other questions? It's saying there's a slope at that specific x coordinate. Mm-hmm. All right. Any other questions? Okay, so do we need to look at Larson 75 through 70 or 75 through 80 and maybe clarify any of the questions from yesterday? Would that be good? Yeah. Uh-huh. Yeah. So let's look. Or not differentiable because of that specific point that did that specific thing. Yeah. Yeah, let's clarify. Okay. So it says describe the x values at which f is differentiable. So here it's going to be, for 75, it's going to be everything except for what?
Oh, so it's basically like ignoring apart
everything except for, except for x equals, oh, I said 2, but I really meant 3. That's so funny, my answer key. Let me fix that. Everything except for 3, and then why not 3? Because there's a discontinuity there. Yeah, so we're using the reasons on the pink sheet, and the reasons on the pink sheet are discontinuity. Okay, so for 75, it's not differentiable at 3 because of the discontinuity, but it's differentiable everywhere else. I'm not worried about anything else, but the 3 is the issue. Okay, for 76, what is the issue? X equals -3, x equals +3. What's the reason? Yep, corner or cusp. Typically, people group those together because they're so similar. Okay, corner or cusp. All right, 77, what's the issue there? X equals -4, so it's differentiable everywhere else, just not at -4 because corner or cusp. 78. No, but we don't talk about y equals, right? So y equals is, we've got the difference between an independent variable versus a dependent variable. y is dependent, so it's gonna, so you say what's happening with the x's, and the y is just gonna happen because it happens. So you are right to recognize there's a horizontal asymptote there, but we don't even have to mention it, because as soon as we mention the x's, the y is gonna happen as it will. Does that make sense? So we say what x's we're allowed to use, and then the y's will follow suit and they'll do the right thing. Okay? So we say it's not differentiable at x equals -2 and +2 because why? There's a discontinuity there, okay? For 79, what do we say? X equals 1, why? It's an endpoint, and so what's the real reason? What limit? The left-hand slope does not equal the right-hand slope, right? There's a right-hand slope there, but there's no left-hand slope there, okay? So it's the idea behind a corner or cusp. It's the same, but technically it would be more like a discontinuity because the endpoint, we're not continuous at endpoints. Okay. All right, and then for 80, what do we have? X equals 0 because the slopes don't equal, and then what's the reason on the pink sheet? Discontinuity. Jump discontinuity instead of infinite discontinuity that time. Cool. Nope, discontinuity. They just say discontinuity. Yep. All right. So at this point, we should be pretty good about the assignment from yesterday. We got the packet. We just went over the Larson. That was my bad. I apologize for not having you guys ready for that. Okay, cool. Yeah, so, okay, so remember yesterday when we found derivatives, you'd say, okay, I'm starting with the curve. And then I would do the long process and I would end up with an equation. And that equation would say, okay, this is the derivative of that curve. And the derivative represents an equation so that if I want the slope at 2, I can plug 2 into the equation that is the derivative. And then that number that I get is the slope at 2. Or I can take the equation of the derivative and I can plug in 5 and I can get the slope at 5. Or I can take the equation of the derivative, I can plug in 7, I can get the slope at 7. Or I can take the equation of the derivative, I can plug in -9, get the slope at -9. So it is saying that when you have a curve, you have an equation of a derivative, which will give you the answer of the slope at any point for that curve. Because when you plug in a number, that only gives you the slope at one spot. The equation will give you the slope at any spot you want. So when we find the equation, we're saying I can get any answer, basically. So the limit definition of the derivative is what we did before. Then we're saying, okay, we can do it the longhand way, but there really are shortcuts. And today we're learning the shortcuts to find those equations. Does that make sense? And so now what we're entering into is a whole study of all the shortcuts of ways to find derivatives. But the big picture perspective is you have this equation of derivative. If you ever want to know what the slope at a specific point is, you just say, where do I want to know the slope? I want to know the slope at 2. Okay, plug 2 into that equation. And if I graph it and find the line, it's going to have that slope at that curve. And every single time, if you ever want to know, literally pull up Desmos, graph that sucker, it's going to look right every single time. Yep. Good question. All right, so let's go ahead and try. This is Larson, page 135. I'm going to maybe let you guys, what is the first part of the assignment? 3 through 18, did I adjust that at all, or was it really 3 through 18? Okay, I'm going to let you guys do a couple first because the first couple are easier. I'm going to let you do the first couple in your groups and then see if you run into questions. And then when you get down to number 9, let's do number 9 together, okay? Because I think that you guys can work, you do the first couple as like a warm-up. So I'm going to let you guys work on the first few. And then if you have questions as you go, you can let me know. But I think you can do them. And then 9 is the one we'll plan on doing together. So number 4 is using that same rule. It's a constant. So f of x, and the number 4, number 4 doesn't really have two different notations. You can use number 4 as just f prime of x. Yeah, number 3 with y, you could do y prime or dy dx. Those are two notations that go kind of nicely. I think actually another one is like Newton's notation, which has like little dots above it, but like nobody uses that. It is cool, but like nobody uses it, so I don't know. It'd be funny though to go use it on an F or Q, and the graders, they'd be like, "Oh, nobody uses that. That's very interesting," you know. I don't know, yeah. Yeah. Okay, so number 5 uses rule number 8 on your yellow sheet. Yeah, so you take your exponent, you drop it to the front, and then you drop the exponent by 1. So take the 7, move it to the front, and then subtract 1 from it. Do you guys want to do y prime, or do you want to do dy dx? Y prime. So 7x to the 6th.
But that would also be 0.
Yeah. So 7 is a little flashback from the summer assignment. Oh, dang it. You said it, and then I started doing it. And I got distracted. Okay, so we got 1 over x to the 5th, and we have to use the summer assignment and think about, don't say it again, okay? Because Nathan already ruined the surprise for us, the punchline. Somebody other than Nathan. Somebody other than Nathan. What's the trick? Yeah, negative exponents. Because, I mean, you can do it. We talked about the quotient rule in the video, right? The quotient rule is possible, but it's not as easy as rewriting it as a negative exponent. So if we can ever be lazy and rewrite as a negative exponent, that's what we do. No, you can. And we're going to, but we're going to write this as a negative exponent because it's easier than the quotient rule. Say it again. We're going to do it. Yep, we're going to do that. So I rewrote it as a negative exponent, and now I'm going to do it exactly like I did 5 and 6. So drop it to the front. No, we are. Okay, so there's my answer. Now I have a negative exponent. I'm going to go back and rewrite this as a fraction answer. Because I'm... Okay, so now we've got negative 5 over x to the 6th. Okay, we survived. That's nice. Thank goodness you guys were here to catch my little mistake. You're like, Miss Rice, I thought you could subtract. All right, number 8, we got our first one with a coefficient. You guys ready to handle this one? So how do you handle it when so we rewrote it as a negative exponent. How do we handle the coefficient of 3 and the exponent of negative 7? You multiply them. Yeah, so when you find the derivative, you multiply them together. So y prime is going to equal what in the front? Negative 21. x to the -8. Okay. All right, we're ready for 9. Okay, flashback to the summer assignment. How can I rewrite 5th root of x? Okay, x, write my f of x equals x to the 1/5. Okay, so what should I do? Okay, so f prime of x is 1/5 in the front, x to the -4/5. Okay. Okay. So x to the 4/5. What do I do with the 1/5 in the front? 1/5. Okay. Now, if this was 5th root for the original problem, then my answer should probably be written as a radical as opposed to a rational exponent, because the original problem was radical. Uh-huh. 5th root x to the 4th. Oh, I need to have my f prime of x, though. F prime of x equals that. Wasn't too bad, you just gotta be careful. Careful, show your work, don't scribble out if you're in pen and you make a mistake. Take up paper. Okay. Not so bad. You guys got it. Easy peasy. Let me know when you get to one that uses the quotient rule, because we probably want to do that together. You know it's the quotient rule when you're dividing stuff, okay? All right, let me know when you get there.